Okay, so hello and good morning. I warmly welcome you back to the fall edition of the One World Signal Processing seminars. Today we are very happy to have Visa Koivunen from Aalto University with us. So hello, Visa. It is a particular pleasure for me today. I know Visa for almost 20 years and his work has always been very inspiring for me. Before we start, I ask you to mute your microphones if you have not done so. If you have questions during the talk, put them into the chat. We will collect them to address them at the end of the talk in the Q&A sessions. And then you also have the chance to ask further questions. So let me briefly introduce Professor Visa Koivunen, our speaker of today. So Visa Koivunen received his doctorate degree in electrical engineering from the University of Oulu. He was a visiting researcher at the University of Pennsylvania from 92 to 95. And since 99, he has been a full professor at Aalto University, where he is currently Aalto Distinguished Professor of Electrical Engineering. His research interest includes statistical and multi-channel signal processing and their applications in wireless communications, radar, smart grids, and data science. He received numerous awards. He is a fellow of the IEEE and a fellow of Eurozip. And today he will speak about waveform design for integrated sensing and communications. So without further ado, I hand over to you, Visa.
Thank you so much, Marius, for your kind words, and I'm really happy to see that many people were able to join the seminar presentation today, even though I just learned that there's a public holiday in Hong Kong, and obviously people maybe rather go out to the parks and nature than attending a talk. But, so today's topic, it's entitled Waveform Design for Integrated Sensing and Communications. And those of you who are into wireless communications and especially research related to emerging 6G programs and so on, you may recognize this words integrated sensing and communications, because it's a topic area that's been studied extensively right now. It's one of the emerging topics and transformative technologies that might actually take place in the future 6G. So today's tasting menu. So my understanding is that most people attending this talk have basically communications background. And therefore, I briefly will walk you through some of the basic ideas of radar, just that you get also understanding of the other side of the coin, that we have the dual function system with communication radar capabilities, that you would at least remember, recall some of the radar ideas. And then I will talk briefly about the basic idea of system models and so on for this integrated sensing and communication, which basically is the idea is that you would have communication radar systems cooperating. They would be co-designed to do both sensing and communications, and it will also extend all the way to designing hardware and circuits and so on, that things kind of extends everything from information theory to circuit design. So it's a very rich area for research. And I will also discuss briefly what it would mean from the 6G point of view. Then regarding our research, that we've been mainly working on multi-carrier waveforms for this type of integrated and sensing communication and sensing systems. And obviously multi-carrier waveforms, they are used in most current wireless standards. And if by doing our co-design well, we could use similar multi-carrier waveforms both also for sensing. That would, of course, allow us to have a kind of convergence and cooperation of these systems. Then I'll provide some waveform design and waveform optimization examples for the dual function systems, and also address topics related to interference management and spatial methods using multi-antenna systems in this type of applications. There's quite a lot of recent work in this area, and very nice survey articles that you could use as a starting point. Dan Bliss has written quite a few nice papers on this area, and there's a survey paper in the IEEE Access. Then there was a special issue of the IEEE magazine in 2019, and we also had a paper there with Vijay Kumar Mishra and Björn Ottersten and of the others, and also Bones Amin and his team. They've been working on this topic area quite a bit. So and he has also written some nice review survey papers. Regarding these design examples, so I'd like to acknowledge my co-authors that have been had the pleasure to work with, Furkan Kesking and Henk Wimers from Chalmers University in Sweden, Uli Mitra from USC, and Tuomas Maittomäki, Marian Pika from Aalto University, and Yuan Hao Chui from Beijing University. So just to tell you about some of the drivers for this type of research, so the cooperation, co-design of communication and sensing system is usually done for mutual benefit. Or somehow these two functionalities would benefit from designing them jointly and having these systems to cooperate. There's a high potential for getting more efficient use of the spectrum. And also, if you are doing both sensing and communication the same transceiver, there would be a chance to also save in power resources. And of course, power is a very important resource. And if we are going more towards green communications with doing more with less power, so this is of course one opportunity for such gains. Then everybody knows that the spectrum is getting more and more congested, and we will have to share spectrum among different radio systems, and we could even think that the spectrum is even contested in some scenarios. So coming up with techniques that use this radio spectrum in an efficient way so that everybody can get their job done is of course desirable. There's also trends in hardware design, coming up with multifunction hardware and something called RF convergers that you use the same widgets and gadgets, transceivers, antennas, and front-end circuitry and so on for many different tasks. This integrated and sensing communication and sensing systems, they have quite a few interesting applications. One obvious one being the vehicular networks, that cars and vehicles, they would have chance to both communicate among themselves as well as with the traffic infrastructure, as well as sense and where the other cars are, and making sure that the driver and cars are being safe and collisions are avoided and so on. Environmental monitoring is of course one important area that where this type of integrated sensing and communication is a very promising technology. Remote sensing, the Internet of Things, the massive connectivity and so on. Smart cities, figuring out, for example, where you have a lot of people and a lot of activity and so on. Infrastructure like power grid. And one interesting application area is indoor services, for example, monitoring the well-being and vital signs of elderly people who wish to stay home as long as possible, and also using it for user interfaces like the gesture recognition of that Google is doing, and also gait recognition, that you could recognize people based on how they walk and so on. So this would be kind of one of the truly novel technologies considered for 6G instead of just being more of 5G if you think of the future. For us as researchers, there are a lot of exciting research opportunities, starting from information theory, signal processing, mobile computing, radar systems, vehicular technology, hardware, and circuit design. And but you also need to understand both the wireless communications part as well as the radio frequency sensing and radar. So in order to do the job well, it's good to have understanding of both of these functionalities. The examples I will walk through, because we have just limited time, I won't be able to go to really in the gory details. So for those who are interested, then these papers kind of describe these examples and all the derivations and matrix formulations and so on in detail, so that you can get more information about the works here. So and all of these papers can be found from the IEEE Explorer. So a few remarks about radars, and of course the word radar comes from radio detection for detecting and ranging. So you want to detect targets and also estimate the distance from the radar to the target. And a typical radar would determine the range, i.e. the distance, and velocity of the target, and that velocity would be the radial velocity towards or away from the radar, and also the directions of the target and in which azimuth or elevation angle the target is. And this is of course based on the radio waves that you have transmitted, and they are then reflected off the targets and observed by the radar receiver. And there are many different design choices. Radar transmissions can be continuous wave radar, or you can do pulsed transmissions. There are also active sensing, which basically would mean that you are transmitting waveforms and then observe the backscattered waveforms, or you can use passive radars that use signals of opportunity, other wireless systems and so on that for radar purposes, but you are not controlling the transmissions, that you are just hitchhiking to somebody else's radio frequency signals. And there are, of course, a huge variety of applications, starting from just regular radars that measure, for example, the speed of a tennis ball or a baseball that is being pitched, and the policemen want to give you a speeding ticket, all the way to multi-function, fully adaptive cognitive radars that you might have in a battleship or fighter jet. It's important when we are talking about this type of dual function systems. It's also important to recognize that the signal-to-noise ratio in a radar signal is different from that in the communication system. It's a very small difference in the formula in terms of giving the link budget and so on, but very important in the sense that the SNR of a radar signal depends on the fourth power of the range instead of second power. And this is, of course, important when you do co-design and develop dual function systems. Because, for example, if you need to double the radar range or surveillance volume, then you have to increase the power by the factor of 16. And then this kind of attenuation of the radar signal may lead to scenarios where they have a large imbalance between the powers of the radar signal and the communication signal. Therefore, it's kind of maybe more promising to consider this dual function systems in in, in, uh, in uh, short range applications. So the radar signals, they, as I mentioned already, they can be continuous wave radars, and then you can modulate the radars. You can have frequency modulated continuous wave radars, or pulse radars that use something called pulse compression. So you are basically transmitting the pulse, and then you are waiting for the return of the pulse, and then based on the return, you then estimate the range and radial velocity of the target. The important factor in radars is the resolution, because it tells you how well you are able to distinguish between the targets that are very close to each other in range or angular domain. And the range resolution depends on the pulse width or the RMS bandwidth of the radar signal. And so that the resolution is basically the speed of light divided by 2 times the RMS bandwidth of the radar signal. In the angular domain, the resolution depends on the beam width that you are using in the antenna you are using, and that the beam width again depends on the size of the aperture. Basically, aperture is the size of the aperture is defined by the size of the antenna configuration in terms of pigments. And of course, from the resolution point of view, the smaller azimuth range resolution cells you have, the better resolution you will have, and the better also interference tolerance you will have. If you have a co-located receiver that shares both the transmitter and receiver hardware, then you cannot listen during the transmission of a pulse. You need to disconnect from the transmitter during the receiver from the transmitter during the transmission to avoid any damage. And in this type of system, then the radars which have a very long pulse width, for example, in pulse compression systems, they have a relatively large minimum range, and so there's kind of minimum distance that you can measure, and that depends on the pulse width. And this pulse length in the pulse radars, they can be of the order of tens or even hundreds of microseconds. Then when you talk about the accuracy of the radar, so it's different from resolution. Accuracy basically just gives you the probabilities that, for example, if you think of 95% confidence interval, that the target is within certain range cell or range azimuth cell. So that's more like a statistical measure. So radars, they have a lot of different sensing tasks. The simplest ones being that you search for targets and then detect them, for example, by using a matched filter. Then you need to determine the target range, which is of course obvious, and the velocity and bearing, in which direction the target is going to. And if you have done multiple successful detections, then you really want to track the target. And then if you have targets that are doing some maneuvering, or if you have multiple targets, then you need to deal with those as well. Then you might be interested in target parameter estimation, and in many applications, you might need to estimate the radar channel, especially if you have an adaptive radar system that will adjust the transmitter parameter based on the target returns and signal to interference noise ratios and so on in that it's experienced. It's very important also for radars to estimate the noise and interference statistics, and those are used especially in detectors in order to come up with constant false arm rate detectors, because it's a big problem for radars that if you get too many detections, then your radar will be overwhelmed and you cannot do the jobs you need to do, and therefore very strict control of false alarms in detecting targets and then taking them into tracking is necessary, and that is achieved by smart estimation of noise and interference statistics. Then you might want to do target recognition, especially based on something called high resolution range profiles. And many of these human activity related applications, you would estimate microdoppler signatures and use them to, for example, figure out heart rate variability or how person is moving, or if he or she is not able to move, like in case of elderly person falling down, and then you would, based on the microdoppler signatures, would be able to tell that, okay, this person really needs help. And of course, if we are operating in shared spectrum environments or even hostile environments, then we need to be able to mitigate unintentional as well as intentional interference. And many of the modern radars, they use something called waveform diversity. They're able to use a variety of waveforms and optimize them and allocate powers and so on based on the kind of returns and channel awareness and interference awareness they have. And with this type of integrated sensing and communication, then you of course are dealing with the multifunction operation. Multifunction operation is already common in military radars that you might have. The radar would have capability to do a variety of radar tasks. Then it might be able to do communication at the same time, as well as some electronic warfare tasks. But of course, these military radars, people are not interested about the price of such radar, but just about the performance in extreme conditions and hostile environments. But of course, obviously, we are more interested how to make these things work in civilian applications and make sure that the price of these systems remains reasonable. And furthermore, of course, radars, they need to deal with unwanted echoes or returns. That's usually called clutter. Just like in communication signals, radar signals are subject to multipath and different sources of interference. And here are some examples of radar systems. This is the upper left corner. There's this Google system for recognizing gestures and using it as a user interface. Then we have a weather radar here and weather radars usually are using polarization extensively to figure out different weather conditions. And then this is some work that we did on recognizing or estimating vital signs, heartbeat and breathing of a human based on the microdoppler signatures and time frequency analysis. And that's something that we did with Nokia about 10 years ago. And then, of course, one of these most promising areas is this vehicular applications that cars are equipped with multiple radars, and then in order to detect pedestrians, bikers, other vehicles, making sure that everybody's safe there. And then on the other end of this radar technology are these military radars. There's a kind of electronically steerable array system in front of the fighter jet, and this is a kind of picture of a very modern radar concept that's a fully adaptive cognitive radar system that can fully adapt its transmitter and receiver and use MIMO radar technology, launch many different waveforms simultaneously, having multiple tasks, and it will be also using the understanding spectrum awareness in order to adjust its operational parameters. So that will be the very other end of the radar systems, and these are of course being developed in the radar community right now. But then it's maybe a bit of an overkill for integrated sensing and communication systems. And here's one example about radar target recognition based on these high resolution range profiles using MIMO radar. That's also work we did quite a few years ago. One additional property of radar signals is the ambiguity function. So it basically gives you the correlation of your radar waveform with the delay and Doppler shifted copies of itself. So it's a two-dimensional function of delay and drop. And this ambiguity function, the idle ambiguity function, has the shape of a thumbtack shape, which is kind of looks like an impulse in the zero Doppler and zero delay point of this ambiguity function. And of course, that's the kind of type of ambiguity function we like. We would like to have waveforms that have this type of ambiguity function, because it would allow us to distinguish the correct distance to the target and its velocity there. Of course, radar channels are also something that people have to deal with. So, and radars are subject to many different propagation phenomena, just like wireless systems. And this kind of channel models, or these fading models, they are called swirling models. These swirling models are somewhat outdated in the sense that some of them are based on this idea of mechanical scanning with the radar. So there's like a periodic scan period when this kind of the reflections and scattering changes. And with modern ISA radars, the radio environment has become way more dynamic. So, and there's no periodic scanning. Scanning, the beam patterns change very rapidly, just like in the wireless communication MIMO systems. And it's also important to recognize that target is a part of the radar channel. So it's maybe a rich scatterer. If you are in a very far distance and a small target, then it's more like a point target, whereas if it's a large target, a target like ship or so on, it would be an extended target. And this channel awareness and so on, it's very important when you optimize the radar waveforms, also in the case of these ISAC systems. When you do resource allocation, you want to put your power and to resources where the signal is propagating well and get strong returns, and you indeed will need some information on the channel state, and that is typically obtained through estimating the channel, getting feedback from the receiver, or based on channel reciprocity. Also, the kind of a type of target is also important. So the how much the target reflects radar energy, it's described by radar cross section, and it's measured by square meters or decibel square meters. And it's an example of a radar cross section for a fighter jet. That if you illuminate that jet from different directions, these are the kind of what kind of responses you will get. And this is not a stealthy target, even though the front returns are weaker than from the side, but the stealthy target would still look a bit different. And there are, of course, different radar configurations, monostatic MIMO radars that may be co-located or distributed, and so on. One important thing is that you need to be able to kind of protect the radar from self-interference and make sure that the transmit and receive antennas are well isolated. And of course, one really promising technology for that would be the full duplex transceiver structures. But for many applications right now that they're still in the kind of prototypes, studied in the labs and so on, and also price might be a kind of showstopper in some of the low-end consumer applications. And then in such cases, people might resort to bistatic structures and so on. One should achieve about maybe 100 dB over all isolation, and so that you could transmit and receive continuously with this type of dual function system. And then there are also a lot of issues with duplexing of these systems, whether you are doing it in time domain or frequency domain. Of course, for radar, you are of course getting the returns in the same frequency, and then of course we have multiple different radio systems, how to do the multiple access and then how to multiplex signals. Okay, so that was just a quick and dirty words about radars, but so these ISAC systems, they should actually be co-designed to get the full benefit from doing both sensing and communication. And obviously there's need for system models for that purpose, different techniques and implementations that will jointly optimize the performance and waveforms of such systems. Also systems that manage the interferences and use this shared multifunction hardware and share antennas and resources, beams and frequencies in a harmonic manner. And one difficulty being that the spectrum is varying very rapidly and it's shared and congested and so on. And then also the frequency regime where you're operating plays a role. So for the propagation phenomena at sub 6 gigahertz frequencies are very different from those at the 77 gigahertz bands. Then I walked through you quite a few different radar tasks, and then it's important to remember that the performance criteria and the resource requirements are very different in these different tasks. So in communication, usually you have to basically maximize the rate or give a certain type of quality of service and so on. But in radar, there's a really multitude of different tasks, different performance criteria. By using this type of system, integrated system, then of course one way to design the system is to try to make it orthogonal. And so could you think of using orthogonal subcarriers, orthogonal codes, orthogonal beams, then doing the design in time domain, using time slots there, and then making sure that the interferences and the signals of interest, they live in different spaces. The design precoders and decoders, or both of them, just to make sure that you are experiencing less interference, and also using different sources of diversity, polarization, frequency, spatial diversity, and so on. These signals, when you launch them from the transmitter, they may be orthogonal, but in many cases they are, when they actually reach the receiver, they are not orthogonal anymore, and therefore, of course, receiver processing also is very important. And there are a variety of techniques to deal with such cases, using mismatched filters instead of matched filters, really exploiting the channel state information for optimizing the waveforms, taking advantage of feedback, feed forward, or reciprocity, and all these precoder and decoder designs to make sure that the signals are projected to different subspaces and no interferences and so on. And if both radar communication you are using digital transmissions, then you could also use interference cancelling receiver structures to take care of the receivers or the interferences, and that will also work if you have a power imbalance between the radar and communication systems. So some of these ISAC applications, so automotive systems, are of course a very promising one, and we wrote a paper in the magazine on those topics, and the smart homes and elderly well-being, microdoppler analysis of motion, human motion, and so on and so on. There are quite a few applications there, and in like a consumer products, you could also think of the coexistence of these systems with the Wi-Fi access points and that are performing communication indoor localization, as well as this type of radio frequencies. Because one promising application would be use this type of integrated sensing communications in drones and UAVs, because it would lead to reduced payload, improved energy efficiency for a variety of applications. And of course, this payload is a big issue in UAVs, because they are usually battery operated devices, and they want to extend the lifespan and so on for as long as possible. I already brought up the issue that there may be more potential for shorter range radar applications, because if you really target long-range applications, then these power differences between the radar and communications would be significant. And of course, this high powers also usually mean high interferences, and also these power differences basically would require more isolation and advanced interference management techniques. And just to give you an idea that indeed doubling the surveillance range of radar that could require using 16 times more power for the transmission. So here are some examples of these radar integrated sensing and communication scenarios that you could have a co-designed dual function radar communication system here. And you might have a communicate or collaborating communication system, and there would be chance to share, for example, channel state information between these two guys. Then we have a target vehicle, aircraft, or whatever it is. Then there might be communication systems that are causing unintentional interference, for example, using the same frequencies reuse the same frequencies in different locations. So, or you might get some interference from the adjacent bands and things like that. And then, of course, there may be sometimes some adversarial activity that you want to protect yourself from. And here's an example of a vehicular application where the cars would have the sensing and communication capabilities. There would be also integrated intelligent reflective surfaces could be used in this context to make the propagation environment more favorable, and then different type of platforms for sensing. And this example of where these systems are used for monitoring human motion, book by Mones Amin and edit book, and there are some nice examples there. I mentioned the vehicle application already, and of course this is also very nice source for applying machine learning, that you actually learn how to, for example, allocate your resources, and this work that we did on using partially observable Markov decision processes and reinforcement learning to find optimal power allocation for both radar and communication task. And so example of like a water filling power allocation for the radar. So regarding this ISAC system designs, that these modern communication sensing systems, they have a number of degrees of freedom and operational parameters, and then you can adjust those parameters to optimize or maximize the performance criteria that you are using. In communication, sum rate is typical criteria, and in simple radar tasks, you use this constant force rate detection as a performance criteria. And then these technical challenges is how to design these waveforms, how to do interference management, and how to do high resolution spatial temporal processing to distinguish between users and targets and so on. And in shared spectrum, of course, these multi-user and multiple access issues are important and need to be addressed. All right, so a few words about ISAC and 6G. That my view, and some people share that view, that 6G should not be just more of 5G. And there should be something really genuinely new, transformative technologies there. And one could think that ISAC, it would be have a high potential to be one of such technologies. The other techniques that are being considered are these intelligent reflective surfaces, so free massive MIMO, and this optical and terahertz communications. Standardization in the area of integrated sensing communication would be necessary to ensure companies and R&D organizations and so on, they are investing on this area. One issue is, of course, that usually when you do standardization wireless system, you standardize the transmitter and not the receiver. And then when you have many different tasks and so on, it may be difficult to come up with a standard, because stuff you transmit or signals you transmit depend very much on the sensing task. That vehicular radar would be very different from monitoring elderly people at home or some assisted living. So the performance criteria would be very different in those different tasks. All right, so then that was kind of maybe more about the general idea of ISAC, and then let's go to some design examples. So, of course, most wireless systems, they use multi-carrier modulation, and that's well, multi-carrier modulation is also being used in radar systems, maybe starting from early 2000s by work on Lebanon, MCPC radar waveforms, and then 2006 and so on Genderen, and currently there are of course radars that use OFDM waveforms, and especially passive radars that are based on digital TV transmissions or digital audio transmissions or Wi-Fi. And in this case, we have no control over the transmitted waveforms, but we are using somebody else's signals of opportunity to operate our radar. Multi-carrier waveforms, they bring many advantages of conventional single carrier radars. So obvious one being frequency diversity. It also allows you to interference avoidance and allocate resources to different subcarriers. The additional benefit is that you can actually estimate the Doppler using just single pulse, and instead of using multiple subsequent pulses. And this broad bandwidth that the multi-carrier signals usually use, it gives you also high range resolution. You recall the expression for the range resolution through the RMS bandwidth. It also gives you a nice way to control the interferences and so on. So there are many ways to design these systems in an orthogonal manner. The subcarrier spacing and so on is of course designed so that there would be no intercarrier interference. Then you can do multi-carrier spectrum type of systems and apply orthogonal codes along the subcarriers and so on. Or you can even go further and apply long scrambling codes that really reduce interference between the radar communication subsystems. And an additional benefit is that there has been a lot of effort in developing transceiver structures for multi-carrier systems, and you could use the similar hardware as in communication systems. And in most recent works, you have also massive multi-antenna configurations there. So there's a lot of the building blocks you need for this integrated operation are present in a modern communication transceiver. When you use multi-carrier transmission, of course, the major drawback is the high peak to average power ratio. And typical radars, they would like to transmit constant modulus signals so that you can use the amplifiers in a very efficient manner, and as a result, get longer range, longer coverage for the radar, a larger surveillance volume. Okay, so some design examples that we have. So first of all, this type of generalized multi-carrier model for radars. That in 2014 we designed this matrix model for multi-carrier radar and communication. That same matrix model would apply for many different cases, and most of the well-known systems would be special case of this matrix model. And the model would allow you to do coding, spreading, power allocation, subcarrier selection, and so on, using the same model. And then if you think of many of the radar waveforms, continuous wave, FMCW, all these chirps and frequency hopping, and this Lebanon's MCPC, OFDM, multi-carrier DSCDMA, and multi-carrier CDMA, all of these would be special cases of such a multi-carrier radar, generalized multi-carrier radar model. And then that's just some description how these different models would fit into this generalized model, and examples that these step approximation of these chirp signals or frequency hopping signals, and so on and so on. And then from the radar point of view, be important to check always that how does this ambiguity function look like, so how well I can distinguish the target in delay and Doppler domains. This is a simple design example how to allocate powers to the subcarriers when you have this joint radar communication task at hand. So this would be start from the radar performance, that you want to design a detector that based on the Neyman-Pearson principle, which tells that you want to maximize the detection probability subject to the constraint of the force arm probability. And then you have additional constraints to ensure that the also communication system gets its desired performance. So you basically define a constraint on the minimum rate requirement for communication system, given here with this logarithmic expression, where this circled expression is the signal to interference and noise ratio. So we need to have a rate higher than certain rate, and then also you have some constraint on the maximum transmit power for the rate. This problem is a non-convex problem, but there are then backup tricks that you can find actually from that paper how to solve this problem. Another example is how to use pulse compression or spread spectrum, multicarrier spread spectrum model for radar system. And the idea here is that on each subcarrier we would transmit a direct sequence CDMA signal, and then of course that how much spreading you do, that would also impact the intercarrier spacing. And then you would allocate this certain subset of subcarriers to the communication system and another subset of subcarriers to the radar system. And for the communication part, you could use orthogonal variable spreading factor type of design, so you get different rates for different subcarriers depending on the rate requirement and quality of the channel gain on that subcarrier. And then you can of course make these code designs orthogonal, so there would be little interference between the subcarriers. But if you then want to have additional isolation between the radar and communication system, then you could use the kind of long scrambling code on top of the radar part and on top of the communication part, and that would really isolate these systems from each other. And this idea is very similar to what is used in 3G and wireless wideband CDMA systems, that you would have like a long scrambling code isolating sectors or base stations and so on from each other, and therefore there will be less interferences and correlations among the signals. And there's on the right this example of the ambiguity function of a waveform produced this way, and it looks very much like the ideal ambiguity function with this thumbtack shape. Then our more recent work that we did with Furkan Keskin and Henk Vermeers is it's kind of limit feed forward waveform design for this OFDM dual functional radar communication systems. And so the idea is to optimize subcarrier powers for both radar and communications in the time frequency domain. And we will have a radar optimal design for this dual function waveform. And the idea there is to minimize the parameter bound on delayed Doppler estimation, and with a constraint on the integrated side lobe levels of the ambiguity function. So the integrated side lobe level basically controls how much power you have on this side lobe outside the main lobe, and you can impose a constraint the maximum of that side lobe level, which of course ensures that you can do a good job in detecting targets with different delays or different radial velocities. And when you formulate this problem and eventually you come up with an optimization problem, that's a convex concave procedure, and a non-convex fractional program is used to solve that. And if you go back to this paper, you will see how the actual solution is found. And then there is also effort to optimize this waveforms in order to get the desired communication rate and whereas the constraint radar will be the similarity constraint. In order to do that, we are using a low rate feed-forward channel, and the transmitter will send feed-forward information through a low rate communication channel to the receiver, and then the receiver will be able to do its job better. And then we have a variety of techniques to solve the problem, exploiting the sparsity and rank one structure of the waveforms, or then the actual optimization problem. Since you're optimizing both the waveform and the control signal, you can do the optimization in an alternating manner. And this approach gives you significant capacity gains over the traditional approach where you use uniform power allocation on the subcarriers without any feed-forward capabilities. And similarly, you get significant gains in delay and operator estimation performance and under this constraint on the integrated side load levels. And here's just figures about the estimation performance here in the lower left corner. You get very close to the Kramer-Rao bound at the different when different ISL constraints are applied. And then the capacity gains, they are illustrated on the upper right corner in the case of range estimation, as well as the velocity case. So there's a kind of a significant capacity gain in the communication part when used this optimized waveform compared to this uniform power allocation no feed-forward system design with this green dotted line. So that's another example how to do this waveform designs. And then one additional design example is that how to kind of use mutual information based on criterion to come up with a compound objective for radar and communication tasks. So we have a mutual information expression for the radar, and that mutual expression is between the received target signals reflected off the targets and then the impulse response of the target. And whereas this communication system wishes to maximize the mutual information between signal at the communication receiver and the transmitted signal. And then you have this joint criterion that you wish to optimize, and then if you wish to weight these guys in a particular manner, that can be also done. And then you could also have a different design problems, whether you want to emphasize the radar performance and use the communication system as a kind of a sidekick, or vice versa. What this design does is basically based on this radar and communication channel gains and mutual information expressions. It will do subcarrier selection. So, for example, this case, the subcarriers with a green dot are selected for communication purposes, and the subcarriers with the blue dot are selected for radar purposes. And then the channel gains are visible there. That you see that in the areas where the radar channel gain is high, then you select those subcarriers for radar purposes and allocate a lot of power on those subcarriers. And in the areas where the radar channel gain is small, then you can put more power on the communication subcarriers and communication tasks. One additional constraint here could be that you recall that the radar resolution depending on the RMS bandwidth. So you might want to put power on the edges of this multi-carrier system so that you get larger bandwidth and higher range resolution that way. So that could be written as an additional constraint. Then you can do also special methods, beamforming and so on. And beamforming, of course, is slightly different, whether you're operating in 6G or sub 6 gigahertz frequencies or 77 gigahertz frequencies. Again, you can have a radar-centric design where the communication device transmit on the side and try to make sure that the radar is not suffering, and your communication systems maybe is less important, but you can provide some low rate communication with them. And if you design these beam patterns for the transmitters appropriately, then you can transmit these communication signals either using amplitude, phase, or both in the side lobe signals. And there's a paper by Hassanian from 2019. And of course, phase shifting is nice because it doesn't impact the transmit power. And then you have different design criteria, whether you want to have exactly the desired beam pattern, you want to maximize the detection probability for the radar, you want to maximize the signal to interference noise ratio, or you may have an impose a constraint on the data rate for the communication. Regardless of these different criterion, you need to estimate the channel because that allows you to do this adaptation. If you have multiple users in the system, then of course this phase shifting type of design is complicated and harder to come up. And there are also joint designs by Jonina Eldar and her team, where you do kind of pre-coding of this radar and communication signals, and you do this transmit beamformers, and so in order to ensure that the signal to interference noise ratio exceeds certain threshold value at each receiver, and then you can impose total power constraints as well as per element constraints for your multi-antenna system. Again, you end up with the optimization problem that may be solved by using semi-definite relaxation. And there are a number of different designs, and one additional design I would like to point out is instead of using matched filter at the receiver, you could use mismatched filter design in the shared spectrum scenarios, and this is designed by Tuomas Aittamäki, where you kind of control the side lobe level, integrated side lobe levels, and instead of using a SNR as a kind of maximization criteria for the matched filter, you do the design so make sure that the SINR remains high enough, and then at the same time you can kind of control the cross correlations around the different waveforms that are present in the system. And here the kind of a receive filter output for regular match filter is given in red color here, and then this mismatch filter that can control this response at different delays. So make sure that the response is low enough and different delays is given in blue color. So in this type of shared spectrum multi-user scenarios, this is a very helpful. I'm afraid I'm probably running out of time, so we have one additional design here that is basically using it's a uniform linear arrays and performing a parameter estimation of MIMO FDM radar, and that allows you to do basically estimate the delay Doppler and angles for different targets in 3 stages that you figure out these angles using music algorithm, and then you do joint carrier frequency offset and channel estimation using this APES beamformer, and then finally delay Doppler recovery from unstructured channel estimates. And the idea here is that you could basically, even if these targets would have the same angle or same range but different Dopplers, or the same anyway, even if the 2 of these 3 are the same, then you could still resolve these targets and so on, kind of get improved performance that way. It's just the stages: first the angle estimation, and then this CFO and channel estimation, and then you can finally figure out that okay, with this velocity and range there's a target, but if there would be in this same angle with just with different range or with different velocity, they would be resolved in this approach. So you can, by using these 3 different factors, you can resolve those targets, and 2 of those factors would be the same. Okay, so then some work we have done on interference alignment based kind of interference management in this joint system. The idea is that basically you just design precoders and decoders in a cooperative manner for the radar communication systems and align interference into very small dimensional subspace. You kind of have this junkyard subspace that you steer all the interference into that subspace, and then the rest of the space is used as a single space, and in order to make sure that you get interference-free radar operation or communication operation. And then we have designed multiple different criteria, design our maximization of sum rates based on mutual information formulation, and then some kind of rank constraint, rank minimization, problem formulation for the same objective, and to find a more efficient solution. There are many different designs. Some of them are precoder designs, and use this beautiful idea of Jafar to come with the interference alignment design. Here's just some of the examples, but in the interest of time, I'll just skip these things. So just to wrap up, so in this integrated sensing and communication domain, that there are tremendous research opportunities for radio frequency sensing and wireless comms. So there's opportunity to do really world-class quality work and have a high practical relevance at the same time. And this is, of course, an area where these radar people, communication people, and hardware and circuit researchers to join their forces to get these things done. And of course, the idea is that you come up with a co-design of sensing and communication and in the hardware domain and RF domain, it's like a convergence that you can do multiple different functions with the same hardware and RF circuitry. And it's also important that to understand not only the communication part, but the sensing tasks and the different performance criteria that are associated with different sensing tasks. And also, in order to make this part of the 6G and make sure that there's money put in the research and development, so it'd be important to have standardization effort related to this activity, and I think this will be maybe one of the study items in 6G and recognize one of these kind of technologies that would really bring in something new into the 6G. And in some other application areas, like vehicle applications, the car manufacturers, they're using proprietary solutions, and of course there's a lot of industrial politics involved. That also some upscale car manufacturer want to give all these technologies and designs to somebody who's really producing the cheapest cars and so on. Because that will kind of distinguish these pricey cars from the not so pricey cars, and of course it's a part of the kind of a brand that to keep this high tech idea and high tech brand image with certain cars. So with that, this concludes my presentation, and I'd be happy to entertain any questions. Sorry, maybe the beginning part took too much time, but since most people have been concerned only about the communication part, I wanted to also bring in the radar into the picture and tell what that brings into the table and how it should be taken into account in this integrated sensing and communication applications. So thank you for your interest, and I'm happy to answer any questions you might have.
So thank you, Visa, for this very nice talk. There has been quite some discussion going on in the chat, and I also want to bring this up here. So, yeah, I would like to ask my colleague from TU Ilmenau, Rainer Thome, to ask his question. He has actually several questions and also comments. So maybe can you please speak up? So we agreed on this before.
Okay. Good morning. Can you hear me? Yeah.
Yes.
Yes, I hear you.
Thank you very much. Okay, hi Visa, nice to meet you again.
Yeah, good to hear from you.
Okay, I really enjoyed your presentation, since I also like the topic of integrated or joint communication and sensing. And I was observing your work at least since the thesis of Marian Pica. Maybe my remark and question, maybe it's a little bit a mix, is that obviously, or at least my impression is that very often joint communication and sensing is discussed from a point of view where still there is some separation between communication and sensing, which means, for instance, if you have a base station, that the base station at the same time communicates, but at the same time, parallel, it uses the RF interface to transmit separate orthogonal radar signals, or may use backward reflected communication signals. But when I started with communication and sensing, or think about communication and sensing, I immediately started from the idea of passive radar. Of course, passive radar, as it is originally, has nothing to do with communication, since we have two separate sensors, transmitter and receiver. But if you start integrating the transmitter and receiver in the same network, you can do the similar things with passive radar. I mean, you can use the signals, the communication signals, as signals of opportunity, but at the same time, you can also modify it, since the sensor and the transmitter are talking to each other and can optimize, mutually optimize. So the advantage would be, I mean, it is immediately bistatic or multistatic, which has several advantages in terms of detection probability in radar. You can completely avoid the full duplex requirement, since you have widely separated nodes. Yeah, though you have immediate access to it. I mean, it is more towards a distributed networked sensing. But of course, you may also have a disadvantage if you would like to see it. I mean, for instance, you are more restricted with the signal design to communication signals. I mean, you could think about using the signals as defined, for instance, in the 5G numerology, and try to adapt it for radar. And I mean, you would have some problems, multiple access problems, sparse distribution of the resources in time and frequency. You can not make a free signal design. You can talk about, I mean, the resource allocation is some type of a signal design, and you could also do pre-equalization, pre-distortion in a similar way. Okay, but it is, from my point of view, it is still a little bit different approach than that first one, which I have mentioned. So, what do you think about that relation between?
Well, of course, this passive radar idea does not necessarily require that you have co-design or cooperation. That any other signal, but of course, if the systems are co-designed for mutual benefit, then it basically means that you need to have mechanism for sharing, for example, channel state information, and also this co-design allows you to use the hardware and spectrum maybe more efficient manner, and then, but of course, it's requires also coming up with these protocols and so on, that how this information is shared, because everything depends on your awareness of the state of the spectrum and channels, and that gives you the tools for optimizing the system performance. But this passive approach basically does not require this co-design. You could use any single opportunity for the sensing task.
Therefore, I am calling it cooperative passive coherent location. Of course, the passive radar guys say, okay, that is not passive, no longer passive radar. But the idea still is to reuse or make a double use of the communication signal. And that is the advantage. So you have a real double use of the signal. I mean, from my point of view, the resource and the exploitation of the radio resources is more efficient than sharing the resources to different to orthogonal signals for communication radar.
Well, kind of hard to tell. Maybe it depends on the particular shared spectrum scenario and so on. But there's this. There has been a lot of effort in this in general address this shared spectrum problem, and I think the cooperation maybe allows you to get more efficient spectrum estimation than just kind of detecting if there's a underutilized spectrum and accessing that. But if by sharing, for example, channel state information, you can really allocate your powers and not to use powers in the subcarriers or antennas or beams where the signal is not propagating.
Of course, it seems to me a little bit more, let's say, communication centric. I mean, it's always a point where you put the focus on, no? On the communication system, which you apply for a different application, or if you do let's say, complete redesign. I mean, the cooperative passive coherent location is more, let's say, takes the communication system as it is and make as much radar out of it as possible.
Well, of course, in the examples, there were a few different objectives for these systems. You could then take the radar point of view and try to, for example, minimize the crime error bound for the target parameter estimation, or use CFR or Neyman-Pearson detection design, and then give the communication just to ensure the minimum desired rate for that system.
Of course.
So there are many different type of designs. So that and this was an attempt to also bring in the radar part on the table instead of just talking about from the communication.
Yeah. Of course, I very much appreciate it. That's not. I mean, I only describe let's maybe a little bit different approach of thinking. Anyway, I mean, I'm really impressed about this huge task which is ahead of us for, let's say, designing these joint communication radar systems. I mean, that from my point of view, there are so many research opportunities opened now to do that. That is really exciting.
Okay. Thank you.
Yeah.
Okay, so we have more questions here. I invite Christos Masouros to ask his questions.
Hi, Marius. Hi, Visa. Thank you for your excellent talk. I just wanted to raise this issue of security for these ISAC systems and gather your thoughts on it. So now let's say your signal that's for two things. You know, your probing signal is carrying useful communication information, right? So I wanted to gather your thoughts about how important this issue is and what kind of solutions you would have in mind. Thanks.
Well, we haven't really thought about the security. Maybe privacy may be an issue in this application where you do human monitoring of humans and so on, although it's much less an issue compared to cameras, for example, because with the radio waves, you can wear your old sweatsuit and have a bad hair day, and the radar can't tell the difference. But the security, we haven't really put any thought on that. Of course, it would basically mean that you have some way of encrypting these signals, and then it comes up with some kind of key management problems and things like that. So that would be an issue, and the encryption would be done in some higher level of the protocol stack. But we haven't really thought of that. We have done some work on security in the short packet communications, but for the radar part, we haven't done anything. But maybe you have some references that you could share with people.
Sure. No, I mean, my own thoughts is that this is a wide open, topic as well. So integrating, security solutions into this comms and radar, and I think it's an open problem with wide open scope. But thanks very much for your comments on that.
Thank you very much. So maybe the last question, there was a question in the chat that has not been answered. So Chao Hang Song was asking, can you comment on waveform at millimeter wave and terahertz bands? The poor PAPR issue for multi-carrier waveforms might limit the share of bandwidth. Wideband signal carrier waveforms in COM and chirps in radar normally do not suffer from this. Can you comment on this?
Well, of course, first of all, this whole terahertz band, and if you go to, let's say, 77 gigahertz and above bands, that right now there's very chance for this type of digital processing of beamformers and waveform optimization and so on. That will be mainly in the analog processing, especially in the spatial domain. Then this peak to average power ratio for multi-carrier communications, there are of course ways to control that. That there are even some from the 80s. There are even some multi-carrier designs that which have constant modulus. I think there's a patent by Jack Winters from 80s. And then you, of course, you can, since you have a basically almost unlimited bandwidth, and you can leave some subcarriers unmodulated and so on. So in that sense, but I'm not an expert on terahertz communication, so I don't know all the kind of degrees of freedom that can be used there to design waveforms and so on. And of course, this would be very short range communication, and terahertz is often used, for example, for imaging purposes and so on. But so also maybe the applications would be slightly different from those that I've addressed here.
Thank you. So there's one final question by Ataka Lili. So maybe you want to ask this question, or is he? No. Ah, yeah, you're here. Do you want to ask it yourself, or shall I speak up? So it is frequency hopping and millimeter wave signals can be excellent potentials for both high data rates and radar resolution. Would you please explain it?
So of course, you can think of frequency hopping as another spectrum waveform. That's just it's direct sequence approach. It's kind of is faster spreading in the sense that whereas frequency hopping is that you have some hopping code, pseudo-random hopping code, that you jump from one subcarrier to another and transmit there for a while, and then jump to another subcarrier. And then you can of course give each well, you can give radar, and you can give the communication users different hopping codes, so that they would not be in the same subcarrier at the same time. And therefore, and then you just need to synchronize the radar and communication part so that they hop in the same pace. And there are many different type of code designs. You can think of Costas codes, for example, that Costas code is kind of like a permutation matrix that makes sure that you don't have the same column or same row of a matrix that multiple elements are active at the same time, and so that could be one way of designing these systems. And then another way is of course this the kind of direct sequence multi-carrier system that would then have enough bandwidth to give you high range resolution, and at the same time this orthogonal code design would ensure that there's no mutual interference between the radar and communication or among the communication users themselves.
Thank you very much. So Visa, thank you very much for being here with us today.
Well, thank you for inviting. I'm sorry it maybe was took too much time to explain the stuff in the very beginning, and some of the examples that we studied in more detail. But in the slide set, there's this list of references about the examples. So if somebody wants to go into gory details, please upload those papers and study them a bit more.
Thank you. Yeah. So
thank you all for your interest and sticking around.
Thanks. So I thank you all for attending. Let me remind you that next week, next Wednesday at the same time, we will have a talk by Robert Schober on intelligent reflecting surfaces for free space optical communications. So see you then next week. Yeah, and goodbye.